Hi everyone. So I thought I will quickly sort of elaborate on some of the things we discussed in the class today, but couldn't finish due to technical difficulties with the iPad and just lack of time. So we were discussing the binary gas diffusion problem, and I did kind of walk you through all the steps required for you to do the problem and also solve it for your homework problem. But I've gotten some questions since then in office hours, and I thought it would be a good idea to clarify some of those things and to make sure really this problem is clear. It's an important problem for the course, right? So just some context again. This is a binary gas diffusion problem with y equal to 0. We have concentrations of Ca being Ca naught, Cv being 0. As I mentioned in the class today, this is a binary gas diffusion problem. There is no solvent, so we cannot use this assumption of pseudo binary and constant rho. Okay, that only happens when you have a liquid phase and when you have a solvent. In this case, it's just two gases diffusing. Then it is being reacted here at A equal to 2b with a first order reaction at the surface. At this surface, y equal to L, and the system is impermeable. And if you're thinking, when will this ever be useful? Think of it as a catalytic surface, right? A catalytic surface may have A going to 2b, first order reaction, impermeable surface. So all of this is very relevant, for instance, like some application like catalysis. So what we discussed in the class was, because of this, we cannot use the usual conservation equation which we derived because it's not pseudo binary at constant rho. So we said we'll go back to del B by del T plus del dot F equal to BV. Okay. So then we said this is not equal to 0. This is equal to, so del B by del T is equal to 0 because it's steady and there is no volumetric reaction. There is a surface reaction, but no volumetric reaction, or del dot F is equal to 0. Now, at this point, maybe it was a bit fast in the class. I want to emphasize this equation is true for both A and B separately. This is not true just for A or just for B, okay? And when we have a flux F, we know the flux F is a total flux. It includes both convective and diffusive fluxes. So this is actually NAY for B equal to CA and F equal to, sorry, let's just say NA and F is equal to NB for B equal to CB. Okay. So basically we have this total flux of NA and NB. That's why I can write two equations. What are the two equations? And because it's just a 1D equation, I just care about the one dimension. I don't care about the X and Z dimension. So it will just become dNAY by dy is equal to 0. And then I'll use the second, the dNBY by dy equal to 0. Okay. So these are my governing equations. Okay. So this is clear. I hope this is clear. And this is the equations are pretty simple, right? It's steady, so no accumulation, no volumetric generation, so no like BV term. All it is saying is flux, the derivative of the flux is 0, and the flux being the total flux is capital N, the molar flux. And we can simply say that as simply we can just say that that flux is constant. So dNA by dy is equal to 0 means NAY is constant and BY is constant. Okay. These are our governing equations. This is step number 1. Now step number 2 are boundary conditions. Okay. So boundary condition at y equal to 0 are simple. C is equal to Ca naught and Cv is equal to 0. Y equal to 0. Before I forget, I mentioned these are isobaric and isothermal conditions. And because of that, P is equal to CRT. If T is constant, P is constant, C is equal to Ca plus Cb is equal to constant. And that is equal to Ca naught because we know the value at y equal to 0. Okay. So we did discuss this in class that small c is the total concentration is constant. And this is equal to Ca naught. Okay. So now we get C is equal to Ca naught, C is equal to 0 and y equal to 0. Now the second part, which is the second condition, is interesting. And that's the one where we'll do the interfacial balance. So this is you can have N equal to EY, and note EY in this case is going in this direction. Okay, Y is going in the downward direction. So don't forget that. So N equal to EY, phase 1, phase 2. Now, so this is the first condition. So we'll get F minus BVI in phase 1 dot N cap minus F minus BVI n cap plus bs equal to 0. And again, I want to emphasize, now we will write this for both A and B. It's not just some F, it is for both A and B. When I use small b to be CA, I will use the flux for A. When I have small b equal to CB, I'll use the flux for B, okay? So now we mentioned that there is the interface is not moving, so this is 0, and there is no flux outside phase 2, which is out because impermeable. So this, the other flux also goes to 0. So essentially I get, and n is EY, so n dot is EY. So I get F dot EY plus Bs is equal to 0. And this is true for both A and B. For small b equal to Ca, this becomes NAY, right? This is the flux component in the y direction, plus basically R of Rs of species A is equal to 0, and By plus Rs of species B is equal to 0. So this is what we get. Now, we know that Rs of A is minus KCAL, and this value CAL is not known as concentration at the surface, okay? And let's just say Ks, and Rs of B is plus 2KSCAL, plus 2KSCAL. And one thing some of you might be wondering, and I think let's just make sure it's clear, this is actually flux at the surface is this, and so I'll come back to that in a second. But what I'm saying is flux at the surface essentially becomes KSCAL for A, and flux at the surface becomes minus 2KSCAL for B. Now, this is the point where some students get confused about the sign. So we have just followed the convention 1, 2, and it's pointing from 1 to 2. We put the values and we have gotten to this point. Now, please do note here, one thing is important is that the flux of A is positive. And let's try to physically check that. So we know that A concentration of A naught, Ca naught is at this top point, right? This top point here, concentration is Ca naught. And it's getting reduced because it's getting reacted until it reaches the point L. So concentration of A is higher at y equal to 0, lower at y equal to L. So obviously it will flow, the flux will be in the positive y direction. For B, the concentration will be higher at the surface at y equal to L and will be lower at y equal to 0. It's exactly 0, so it will go in the opposite direction. The flux will be negative. So that's why these signs are actually make sense. All right. Now, we got the two boundary conditions as well. So this is boundary condition 1. So we have two boundaries in the system, y equal to 0 and y equal to L, and you need conditions on both at y equal to 0 and y equal to L. So that's why we got two boundary conditions and for both variables A and B. Okay, so we're good there. And now we go back. This is a governed equation. This implies that NAY is constant, right? And this NBY is also constant. Now, what are those constant values? Well, we already just found a value of flux at the L location, right? So that will be same everywhere, because that's the governing equation. Governing equation says flux is constant. Boundary condition says that flux is that value equal to the reaction rate. So essentially what we get by combining, so combining governing equation and boundary condition at y equal to L, we get that NAY is equal to KSCAL and NBY is equal to minus 2 KSCAL. Yeah, so this is what we get. So this is the first point. So this now what we have done is we have first used the basic equation without the boundary condition and we get this. But we still haven't solved the concentration of A and B yet because we haven't really put in the value of the flux. So now let's try to put the value of the flux. So we have two options. So I'll only focus on NAY for now. So option number one is use NAY with CAV minus D rho DAB by MA gradient D omega D by dy of omega A. That's the first one. Or we can use CAV of M minus CDAB by MA D of chi A by dy. And sorry, there is no DAB by MA, it's CDAB. Okay, so we use flux laws. We have discussed this in detail previously, but if you have not, please refresh your notes and just refresh your memory and kind of get familiar with these two. So it's just breaking down into convective and diffusive fluxes. Now, in this point, we can represent everything in function of C and C except the velocities. So velocity, molar velocity is NAY plus NBY by C, because the definition of molar velocity is sum of N I by C. Okay, so we just have NAY by NBY, and we already know it's minus KS CAL, sorry, plus KSCAL minus 2 KSCAL by C, or molar velocity comes out to be minus KSCAL by C. Okay, so first let me just focus on this option. Once again, focus on this option. Okay, option number 1, where you first found the molar velocity, it's minus KSCAL by C, which means that my NAY is now, which I know is KSCAL is equal to CA times molar velocity is minus KSCAL by C. Now this is minus CDAB minus CDAB d chi A by dc. Okay, d chi A by dc. And so d chi A is dCA by C by dy. And my C is constant, so I can just cancel out this term, or I get NAY is equal to minus KS. Sorry, let's just say forget the NAY because we just are at this. I'm just equating these two terms now. So KSCAL to minus KSCAL by C times CA minus TAB dCA by dy. And essentially what you will get is, if you rearrange this dCA by dy to 1 plus CA by C equal to KSCAL by DAB. Okay, this is the equation you will get, and you can solve this problem from here by integrating. We know the boundary conditions at y equal to 0, CA is equal to CA naught, and at y equal to L. Note that I have already used this variable C is equal to CAL, so I'll just put the value of C is equal to CAL, and I can get the expression for CA. All right, this is option number 1. So here molar velocity was not equal to 0, we got some value. Now option number 2 is when we use this part here, this part here. Now here also I do not know my V, so my V, velocity V, is summation of N by rho. Okay, so this is M, so let's just say Na plus Nb by rho, mass flux by rho. This is equal to Ma Na y plus Mb Nby by rho. Okay, so this is just stating the definition of V. Now please note that if A is going to 2b, then my molar mass will also follow Ma is equal to 2mb. Okay, Ma is equal to 2mb. And why is that? Because if Ma is equal to 2mb, we simply have to conserve mass. The molar masses have to follow. So think of it like H2 goes to 2H, right? So the hydrogen dihydrogen will have a twice the molecular mass of hydrogen. Right, so that's why Ma is equal to mb. So if you use that and you will substitute here, then we'll say, we'll take out mb to be common. We'll say 2 NaY plus nby by rho is our velocity, and because NaY is KSCL and nby is minus 2 KSCL, it will come out to be actually mb by rho 2 KSCL minus 2 KSCL, and this goes to 0. So my mass average velocity is actually 0. So what does that mean for now our flux value? So we say, well, my NaY is equal to KSCL is equal to CAV minus rho DAB by MA, rho DAB by MA, d omega A by dy, and this value goes to 0. So amazingly now this goes to 0. So can we show that this is consistent with the other formula? And that's what you do in your homework problem for a slightly different twist. But let me just show you how to do this for this problem. So we know that this d omega y is actually d rho a by rho dy. Okay, and that actually means it's d rho a by dy 1 by rho d rho by dy minus 1 by rho square rho a d rho by dy. Okay, so I'm just substituting the value of, just taking the derivative using product rule for rho a by rho, which means that this term becomes minus rho dab by ma d omega by dy becomes 1 by rho d rho a by dy minus rho a by rho square d rho by dy. Okay, here we can clearly see that this gets cancelled with the one outside, and this also gets cancelled with the one outside, or we get minus dab by ma d rho a by dy plus dab rho a by rho d rho by dy. Okay, I get this by ma also here, and we know rho a by ma is ca, right? Rho a by ma is ca, so I simply get is equal to minus dab dca by dy plus dab ca. Now this is an interesting term, d rho by dy by rho. So this is the term now that we do need to simplify further. We know that rho is equal to ma maca plus mbcb, right? So let me just clarify further. Rho is equal to rho a plus rho b, because ma plus ca plus mbcb. We can make two simplifications. This is 2mb first. So this is, let's take out 2mb. So mb times 2ca plus cb, right? Because we know that ma is twice that of mb. So mb times, and then ca plus cb is equal to c naught. So we know this becomes ca plus cb. This is constant c. It becomes mb ca plus c. So this is rho. So simply d rho by dy is mb dca by dy, and c is constant, so dc by dy is 0, and so d rho by rho is equal to dca by dy mb by mb ca plus c. This goes away, or finally that means if we substitute this becomes minus dab dca by dy is dab ca dca by dy by ca plus c. Okay, and it's not too difficult. It just takes a second. If you rederive, if you just rearrange this will become dca by dy by 1 plus ca by c equal to ks cal, which is exactly the same as you got in the other examples. Okay, so that means two approaches are the same. So I just wanted to walk you through all of these steps because we couldn't do them in class. Is that essentially the problem just boils down to the fact that we cannot use the usual pseudo binary row assumption. So we go back to the basics. We say basically we put the values, its accumulation is 0, no generation, so flux, derivative of flux is 0 or flux is constant. We apply the boundary conditions to find that value of that flux at the boundary, and then we can say that that flux is equal to the same everywhere. Then we have two options. One is the molar velocity or the mass average velocity. Molar velocity is not equal to 0 as is when we apply the formula, but the calculations are much easier to kind of see and get to the same get to an equation. For mass average velocity, the mass average velocity is 0, but because of this mass fraction driving the flux, you have to do some math. I did it a little fast, but hopefully it was instructive, and you saw that we get to the same point. Okay, so I hope this video was useful, and then this helps you solve the homework problem, and I look forward to seeing you all on Friday.